Welcome everyone. Today we are going to talk about the concept of thermostat and barostat in molecular dynamics. In the video about uh, ensemble and statistical mechanics applied to molecular dynamics, we introduced the concept of the ensemble as a set of configuration of the system, that means different positions of the atoms and different momenta of the atoms, each of which specified by the same set of thermodynamic quantities. So we introduced the concept of microcanonical ensemble, where we keep fixed the number of atoms, the volume of the system, and the energy. The canonical ensemble, where we keep fixed the number of atoms, the volume of the system, and the temperature, and isothermal isobaric ensemble, where we keep fixed number of atoms, pressure, and temperature. When we perform a molecular dynamics simulation, when we integrate the equation of motion to obtain the trajectory followed by the atoms in the system, what we are actually doing is describing a system with the same prescribed energy. That means that the evolution, the configuration obtained in time for our system are configuration which have the same energy. That is to say that in a molecular dynamic simulations, where we are only doing the integration of the equation of motion, we are actually obtaining a set of configurations compatible with the microcanonical ensemble. However, especially if we want to compare our results with experiments, for example, we have to consider the fact that experiments are obtained at constant temperature, or for example at constant pressure if you are doing experiment at atmospheric pressure. So we'd like to be able to obtain molecular dynamic simulations in different ensemble, other ensemble different from the microcanonical one. For this reason, there were developed in the past years different models that are able to keep the temperature or pressure of the system constant. And here today we are talking about the concept of thermostat, which is a model included in molecular dynamics simulations to keep the temperature of the system constant, and barostats, which is a model included in molecular dynamics simulations used to keep the pressure constant. Here I'm giving a quick overview of the different thermostats available in molecular dynamics. This is not an exhaustive list. There are others considered in the literature. These are the most studied, known, mainly for historical reasons. All the thermostats are based on the same basic idea. Couple the system with another system that we call the external bath or external heat bath, which is at the temperature that we want to keep constant. The fact that our system is in contact with this heat bath means that by the zeroth law of thermodynamics, the two temperature becomes equal. Of course, we have to assume that our system, that heat bath is big enough to not be disturbed by our system, and other few assumptions. But this is the basic philosophy of thermostats. Uh, this coupling is obtained in different way, and this give rise to the different thermostats presented here. So we have stochastic methods in which we constrain a system variable to a preset distribution function. That means that we are as obtained in Anderson thermostat. In this case, what we do is to replace the velocity of random atoms chosen in the system. That's why it's a stochastic method, with a velocity drawn from the distribution of specific for that temperature. The Anderson thermostat is the thermostat that is implemented in the molecular dynamics codes that you have, and it is the one that will be explained in one of the lab sessions. So I will leave a more detailed explanation for later. Then we have the strong coupling methods, where we scale the system variables to give exact preset temperature. Is represented by the velocity rescaling. This model is called strong coupling because what we are assuming is that the variation of the temperature between given by the contact of our system with the heat bath is instantaneous. So we have instantaneously the variation of the temperature of our system to reach the preset temperature of the heat bath. The fact that the variation is instantaneous is actually not really good. It has some problems. So in the other models were developed, which are called weak coupling methods, where the variation of the temperature to reach the preset temperature of the heat bath is smoother, takes some time, and for this reason are much better to be used in molecular dynamics simulations. The most important of this method is the Berenson thermostat. Finally, we have the so-called extended system dynamics models, the most famous of which is the Nosé-Hoover thermostat. In this model, the coupling between the system and the heat bath is obtained by including external degrees of freedom into our equation of motion. So now the coupling between the system and the external heat bath becomes a dynamic variables that has to be solved along with the equation of motion of the system. Let's have a look now at how the thermostats work. In particular, let's consider the Berenson thermostat and the Anderson thermostat. Since the Anderson thermostat is the one implemented in the code, we will have a more detailed look in the practical session. I will just give you a couple of words here. So let's start by considering the Berenson thermostat or weak coupling thermostat. What do we mean with weak coupling? Why the coupling is weak? We are modeling the coupling between our system and the heat bath by using this differential equation, which prescribes how the temperature varies in time, and we assume that the variation of the temperature in time is given by this law. This is a very simple law which depends from this parameter tau t, which gives the strength of the coupling. As you can see here, if the value of tau subscript t is large, then this whole quantity is small. That means that the derivative with respect to time of the temperature with respect to time is going to be smaller. That means that we need more time to reach the prescribed temperature, which I indicated here as tau subscript 0. That is to say that when tau subscript t is large, we obtain a weaker coupling. Of course, the opposite is true when tau subscript t is a small value. If this quantity is small, then this whole quantity is large. That means that the derivative of the temperature with respect to time is large. That means that we reach the prescribed temperature in smaller intervals of time. That means that the coupling with the heat bath is stronger. For the Anderson collision instead, uh, as I said, the philosophy is the same, coupling the system with the heat bath, but the way we obtain this coupling is different. What we are doing in an Anderson thermostat is that choosing randomly, that's why stochastic, some atoms in our system and just replacing completely their velocity with a velocity drawn from a Maxwell-Boltzmann distribution, which prescribes the distribution of velocity for a specific temperature. So here you can see that this distribution depends from the target temperature T subscript 0. In Anderson thermostat there is a parameter which can be considered as the strength of the coupling with the external bath, and for this reason I indicated it as tau subscript t as well, which gives the interval of time between which we are doing this replacement of the velocities. Let's move on and let's talk about how to control the pressure in a molecular dynamics simulation. In a molecular dynamics simulation, the pressure is obtained by calculating this quantity, which is called the virial, which we are going to consider in more detail in one of the practical sessions. And through the virial, we will be able to control the pressure of the system. It turns out that the virial depends on the positions of the atoms in the system. Therefore, if we scale the positions of the atom of the system, we will be able to reach the pressure that we want. This is a different philosophy from the one used in thermostat, where we were coupling the system with an external heat bath. Instead, in this case, what we are doing is to act on the positions of the atoms through the virial to obtain the prescribed pressure. Because we are acting on the positions of the atoms, barostat are slightly more complicated than thermostat to be implemented, because now we have to act on the change the variation the equation of motions of the atoms to enforce the constancy of the pressure. The barostat can be divided in two main classes. In the first class, we have barostat, which keep the shape of the box constant, and in this case, we talk about barostat with isotropic coupling. This means that if we start our calculation with a cubic box, we end up the calculation with another cubic box with possibly a different volume. The second class is composed by barostat, where we have a variation of the box shape as well as the volume. In this case, we talk about barostat with anisotropic coupling, and that means that if we start with a cubic box, we end up with a more general triclinic box where the edges, the final edges, are different from the starting ones, therefore the volume is different, but also the angles can be different. So we can start with a cubic box with orthogonal angles between the different directions, and we can end up with a triclinic box with not orthogonal angles between the different directions. So among the isotropic barostat with isotropic coupling, we can remember the Berentzen barostat and the Anderson barostat. One of the most famous barostat with anisotropic coupling is the Parinello-Raman barostat, which is also which also defines another ensemble, which is a generalization of the MPT ensemble, which is called N sigma T ensemble, where sigma now stands for stress. Since the pressure can be derived is a particular case, constant pressure in the three direction is a particular case of a more general stress in the system. This N sigma T can be seen as a generalization of the MPT ensemble. So let's talk about the Berenson-Barostat. In the same way as the Berenson thermostat, we have a coupling of our system with an external system that keeps the pressure of our system constant. In this case, we are also talking about strength of the coupling, and the Berenson barostat represents again another weak coupling, weak pressure coupling. Therefore, that means that we are the coupling with the system that keeps the pressure of our system constant is weak. This is represented by the equations reported here, which has the same structure as the Berenson thermostat. So we have the variation of the pressure during time is given by this linear relation where we have the pressure coupling constant tau subscript p, and again when tau subscript p is high we have weaker coupling. When if we decrease the value of this parameter, we increase the strength of the coupling. So how this barostat is applied to change the equation of motion for our system. So here is reported the main idea. So we start by saying that the variation of the velocity of the position of our particle is not given by dr over dt is just equal to the velocity, but is equal to velocity plus another term, which we indicated by alpha times r. So it's proportional to the position. And also the volume of our system is now, the variation of the volume of our system is just proportional to the volume itself through this parameter alpha. Now we have to define this parameter alpha given the expression of the variation of the pressure during time given by the which is the Berenson-Barostat. So to do that, we remember from thermodynamics the expression of the isothermal compressibility, kappa, which is given by this expression reported here, minus 1 over volume of the system, partial derivative of the volume with respect to the pressure. Of course, this is called isothermal compressibility because we have to assume that this partial derivation is performed at constant temperature. So a little bit of algebra. We replace into the expression of the variation of volume with respect to the time the expression of the volume as derivative as function of p. We use the chain rule to obtain this expression here. So now this term here is the isothermal compressibility, and what we obtain finally, if we just express alpha in terms of the quantity that we have, that alpha is given by this term. So now we can replace alpha into the equation of motion, and we have the new equation of motion which express the variation of the position of the atoms during the trajectory that keeps the pressure constant. At the same time, the volume is varied using this expression here, where we know alpha. In the equations of motion that we just derived for Behrens and Barostat, we saw that we need to include another parameter to be able to actually solve these equations. That is to say that we need to know the isothermal compressibility of the system. However, the good news is that we don't actually need the exact value of the isothermal compressibility for every system that we are considering, because the isothermal compressibility enters into the equation of motion only as a ratio with the Behrens and coupling parameter tau. That means that we can use, as is usually done, we can use the isothermal compressibility, for example, of the water, which is reported here, uh, as equal to 4.6 times 10 to the power of 10, 1 over Pascal, and then adjust the parameter tau.